Um, all right. Welcome back to day 60. Um, progressively getting to the end of this session, which is good. So 40 more days to go. That's about a month of making videos, which is a lot. Anyways, so uh, okay. So I plan to solve some linked list questions today. Um, I'll be going over these questions and, you know, explain how I think I solved one of them, which is, yeah, this question right here, but I'll explain the solution. It's not going to be left out, so I'll go over the solution again. But this question is quite, so for me, as I read it, I did not understand it immediately. So it took me about a couple of hours for me to get this question. And at the end of the day, I also looked at some solution to give me you know, a lead on coming up with the solution. But anyways, so it took me about a couple of minutes to solve this problem. Okay, so let's see how so let's read the question. So this is linked list 141, and it says given, the head, giving head the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if the list, right? No, there is a cycle in a linked list if there is some node in that list that can be reached again by continuously following the next pointer, right? Internally, POS, which is pos, is used to denote the index of the node sorry, I don't know. Let me go over this again and read it properly. I just skip a few words there. So giving head the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS or POS is used to denote the index of the node that the tail's next pointer is connected to. Note that POS is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. Now, this question might seem a bit complicated because of the way, some unnecessary information were introduced in the problem itself. But so the only thing we need here is to actually understand that there will be, uh, a cycle if the last node in the linked list has a connection to any node in the linked list. Like, in other words, if the tail of the linked list is connected back to any node in the list itself, right? So, and they will return true if that's the case, otherwise we return false. Now, POS or POS here is unnecessary. We don't need to know. I don't know why they decide to introduce this POS in the question in the first place. To me, it doesn't really make any sense. But the idea is we simply want to determine if a linked list has a cycle in it, which means the last node of the linked list is connected to any of the nodes in the beginning. So again, you can see this node here is also has a circle in it because the last node or the tail node is connected to the head or the beginning of the linked list, whatever you should call it. But these are just two nodes, and this line here, right, is simply the next node of the last node in the linked list, right? So let me quickly walk you through how this works. So I'll come here. Oh, okay. So here I was trying to practice understanding the question, so I'll just remove everything else here, right? So let's keep this here, or I can just write it out. This is 3 2 1, right? 3 2 0 and -4. So here is what is happening. So our node would look like this, our linked list would look like this, sorry. So we'll have 3, right, 3 2 0 and then 4, right? Now in a normal linked list, the last node is usually pointing to none, right? It will have a next value that is set to none, but this time around, instead of having none, right, the next of this node points back to a node in the linked list, right? Which in a sense makes it circular, right? Because there is no end at this point. Technically there is no end because the end has what would have been our end, right, which is this node here, is connected back to another node. Now this node too has a connection, so the connection will keep rotating infinitely, right? There is no end or tail node in this linked list if the linked list is arranged in this form. So how do we so the question now is we want to determine where, if this if this linked list has a cycle in it, right? Now a cycle will be determined if, let me read this again. So let's bring this to this side so that it's closer. So they say there is a cycle in the linked list if there is some node in the list that can be reached again by continuously following the next pointer, right? So now if we follow the next pointer like this from here to this point right? Or let me right on top. So the next pointer to this node is this node here, right? The next pointer to this node is this node here. The next pointer to this node is this node. The next pointer of this node points back to this node, right? Points back to this node. Now the question is, if a node can be reached, right? If a node can be reached by following the next pointer continuously, then it means the linked list is it has a circle in it, right? So now if you look at this very well, let me highlight this part. There is a cycle in the linked list if there is some node in the list that can be reached again by continuously following the next pointer, right? Now how do we reach a node by continuously following the next pointer? Now mind you, it's not just to go round, right? We also want to keep we also want to remember a node that we've seen before, and then when we are able to reach that node again, we then conclude that this linked list is has a circle in it, right? So one way to do this is, just imagine we had maybe two pointers, right? 2 pointers in the linked list, and they are chasing each other, right? One is moving faster than the other. So when we get to a point where I'll just call this, so let me put X and Y, right? X is being chased by Y. Now Y, Y, X is being chased by Y. Yes, S is being chased by Y. X is moving slowly. Y is moving faster. So at some point, X will be caught by Y, right? So wherever the you know uh, X X pointer, right, gets caught by the Y pointer here, it means you know um there is a connection that happened at that point. So there is a node that has been reached by continuously moving the X and Y pointer through the list, which also concludes that the linked list has a circle in it. So for us to do something like that, there is an algorithm called um, the Floyd hair and tortoise algorithm. The Floyd tortoise and hair algorithm. So that algorithm basically uses a slow and a fast pointer, right? So we have a slow and fast pointer. Now the slow and fast pointer are basically you know just like I said here, that I'll have an X and Y pointer, right, chasing each other. The idea behind the slow and fast pointer is that the slow pointer will move slowly, right, and the fast pointer will move, as twice as fast as the slow pointer. Now, if the if the linked list has a circle in it, the fast pointer will catch up with the slow pointer at some point, right? So let's visualize that and see. Now, the fast and slow pointer. Oh, I did not delete this. This is something I did yesterday. So let me just keep that out of the view, or let me just simply delete it. Let me go up, right? Okay. So the fast and slow pointers, right? They both start, you know, at the head, right? So let me do it this way. So S, and this is the fast. So I'll call the fast pointer F, the slow pointer S. Now, the fast pointer will move twice as the slow pointer, right? So the fast pointer will move 1, 2, right? The fast pointer is at this position before the slow pointer would move only just 1, right? So again, that's first iteration, right? In the second iteration, we'll move the fast pointer again. So the fast pointer will move to this point, that's 1, and then back to this point. Now you would think, oh, okay, so since they are at this point, we've already met the slow pointer at this position here, but that is wrong, because the slow pointer has to move as well, right? So you can see it looks like a chase happening, right? So the fast pointer is chasing the slow pointer. So the fast pointer will move twice again, and the slow pointer will move just once. So fast pointer will move from here to here, and then the slow pointer will meet the fast pointer at this point. So this is the point at which, right, at which a connection is made, or a node is reached by moving through the nodes in the linked list. So this is the point where the fast pointer meets the slow pointer. So this node is where the cycle is determined in the linked list, right? It's not just because the last node is pointing to this node here, that this node is the point of connection, or the point where the cycle happens. The cycle happens where a node can be reached by moving by moving through every node in the list, right? So sorry. So for us to determine that, we use the slow and fast pointer algorithm, right? This is a very common algorithm, and you can use it for something like determining the midpoint of a linked list, right? Now, the middle of a linked list can simply be determined if, so imagine, we have a linked list like this. So I'll just say 1, 2, 3, right? And then none here. Now, if we use the fast and slow algorithm, right? Fast and slow algorithm, the slow the fast and slow pointers, sorry. I meant to say pointers, not algorithm. The fast and slow pointer, if we move the slow pointer to this point, right? The fast pointer will move twice as the slow pointer, right? So our fast pointer will be at this position here. Now our fast pointer cannot move anywhere else because there's no more nodes for it to move to, right? And by the time our fast pointer reaches the end of our linked list, or in other words, the last node or the tail node of the linked list, the slow pointer will be at the middle node, right? Or the node in the middle of the linked list. So to determine the middle or the midpoint of a linked list, you can use this method. So simply, set the fast and slow pointer at the beginning and move the fast pointer twice as the slow pointer. And once you reach the end of the linked list, the slow pointer will be at the middle. Once the fast pointer reaches the end of the list, the slow pointer will be at the middle. So back to our question, right? So we are trying to determine the if a linked list has a circle in it. So yes, this linked list has a circle in it because the connection or a node was reached again by moving through the linked list at this position here, right? So this is where the node was reached again by moving through the linked list. So which means this is a this linked list has a circle in it, or cycle in it. Okay, now what if there was no connection, right? Okay, so if there was no connection, right, the linked list would have looked like this. So this would be 3, 2, 0, and then 4, like this, right? 4 will point to none. Now you can see if 4 is pointing to none, our fast pointer will no longer move from this point because there is no other node after this 4 node here, or this node where the value is 4. So there's no more node for it to move to, and there is no way we can reach any node again by simply moving this this f, or this fast pointer here. So by the time our fast pointer is at this position, our slow pointer would be somewhere here. So again, this will not make it this will not contain a circle in it. But if there was a circle, right, we'll keep, the circle could be at this point or the circle could be at this point. It doesn't really matter. We can still look at the next value of this last node, supposedly, but I in technically, right, technically there is no last node, right, because the nodes are connected to each other. So if there was a connection to this node here, right, we'll be able to move our fast pointer back to this point, right, until we connect with we reach a point where the fast node is equal to the slow node, or in other words, they point to the same node at that point in time. So the solution for this problem is here. So I would quickly put it in my files and push it to GitHub for you guys to access it. So I'll just create a file here. This will be called leads, I think, oh sorry, this is number 124 or 141. Okay, so this is LEETCODE dash 141, and this is has cycle, right? Is the has cycle problem. So has cycle, linked list cycle. So I'll call this linked list cycle like this. Okay, so let's copy oh sorry, let's copy the code here. I'd already written it out, but you know what, let's write it out again. I'll simply copy this part here, right, and put it here so I can explode in it. Okay, so let's remove this option now because we don't need it. Obviously we don't need this, so we can do this, right? Okay, so our head is basically an instance of a node or list node class. So which means we'll have access to the cell, the value, and then the next properties, right? But we are not using values here, so it doesn't really matter. Okay, so we can say our slow, we can create the slow and fast pointers. We can set them to the head, so this will be fast, it's going to be equal to the head, right? So we have a fast and slow pointer here, and then what we'll need to do then is to try and reach a point where the next node can be met in the cycle again. So we need a condition, right? We need a condition for moving the fast and slow pointers. So while there's a fast pointer, which means this head is not null, right? While this head has something in it, and the fast pointer has a next value, right? So these are the conditions that will keep this loop or this iteration going. So while this is there, then we can then check, right? We can start moving the slow and fast pointers. So the slow pointer will move by 1, so slow is going to be equal to, by 1 I mean by 1 step, right, into the linked list. So this is going to be slow dot next, and then fast will be equal to fast, right, fast dot next, like this. Okay, so after doing this, we can say so when we get to a point where the fast pointer, right, fast is equal to slow, right, when fast becomes equal to slow, when fast becomes equal to slow, oh, this has to be an if statement, so sorry, if fast equals to slow, then we can then return true, right? Because this function or this method that is part of this solution class here expects a boolean value as a return value, so we can return true here. Otherwise, when we reach the end of the node and there is no cycle in the node, then we just return false, right? Return false like this, and that's about it. So it's still the same solution as the one I did on LEETCODE. So let's see here. Yeah, so it's the same thing. You can test this out. So the test case is here. So let's see all the test cases have been passed. When I submit this, you can, oh, something else happened here. So what's wrong? What happened? So false is true. What? If fast is equal to slow. Oh, I'm moving fast only once, so fast has to move twice, right? Twice as low. Okay, that was my bad. Sorry. Okay, now you can see the solution is quite good. I don't know why this is. I mean, it was the same solution I submitted before, and about an hour ago, the time complex. I mean, the runtime was 83%, and now it's. That's very funny. Sorry, let's move this. It's because of the spacing I added. I don't. I'm not sure, but so it's still the same solution, right? I think there's something wrong with. Let's submit this again one more time. Okay, you can see. I mean the results are not quite consistent, you know, but that shouldn't be a big deal. I mean, once the solution works, that's good enough, right? So here's my mistake. I'm only moving this once instead of moving this twice. So good. Oh, sorry, I'm not feeling fine today. There are some chats in the description. Sorry, my voice is slow. Hello, everyone. What data structure are you implementing? Um, it's a linked list, yes, and my wallpaper, yeah, right. Okay. Sorry about my voice. I am not feeling fine at all. Okay, so let's continue with the next question I have today. Um, I'll try and I'm not. I don't know. Let's carry on with a second the second question. So what's the next question here? The next question would be, let's move this out of the place. Sorry. The next question is hold on, why am I confused? Okay, yeah, so linked list cycle 2, right? It's a similar question to the other one we just solved now, but this question has a bit to it than the other one, right? Because this time around we are not only going to determine. I mean, the prompt or the question is still the same, but this time around we want to return the index, or sorry, we want to return the. Let me just read this. Given the node, given the head of a linked list, return the node where the cycle begins, right? If no cycle, return null. So there is a cycle in a linked list. This is the same as this, right? There's a cycle in a linked list, blah blah blah. So this time around, we want to return the node where the cycle begins, right? The node where the cycle begins. In other words, we would have returned 2, right? 2 is the node where the cycle begins. Now, 2 is not the node that can be reached by, looking at next, right, in the linked list. But 2 is the node where the cycle begins, because the last the supposed last node in the linked list is connected back to 2, right? So let's see how we can solve this one. So first of all, we would need this part 2, right? We'll need to know first of all if the linked list has a cycle in it by simply implementing the other part of our algorithm. Now, when we are able to determine if the linked list has a cycle in it, then we can then go ahead and find out the part where um, the the cycle began, right? So I'm just trying to remove this part here. So I'll still use this to I'll still use this image here. So I mean, let's move the fast and slow pointer to the beginning. Now we know the fast pointer has to move twice as the slow pointer, right? And then, you know, it's like a chase. The fast pointer is chasing the slow pointer, and then, you know, the fast pointer is back at this point, the slow pointer is here, and then the fast pointer comes back to catch the slow pointer, right? So once we are able to determine, so this, by doing so, we will first of all know that you know, there is a cycle in this linked list, right? Now if that works, there's a cycle in the linked list. Now where did the cycle begin, right, is what we want to know. For us to determine that, we simply have to move this start, right, or this slow pointer back to the beginning. Now instead of us to move them, you know, at the same pace, which was moving the fast pointer twice as the slow pointer, this time around we'll simply move the fast pointer at the same pace, right? They'll move at the same pace. So here the slow pointer will move by 1 and the fast pointer will move by also 1, and they'll meet at this point. So the point at which they meet is where the how do you call it, is where the cycle began, right? The cycle began in the linked list. So let me go over that again. We'll have well, first of all, we'll need to determine if the linked list has a cycle in it before we can determine where the cycle begin, right? So to determine where if there is a cycle in the linked list, right, we simply need a fast and slow pointer, right? We'll move the fast pointer twice as the speed of the slow pointer, right? So the slow pointer will move by 1, and by moving we are simply using the next pointer of the current node. So the next pointer of this node is pointing to this node here, so we'll move the slow pointer to this point, and then the fast pointer will be moved twice as the slow pointer, right? So 1, 2, right? And then we'll move again, we'll move the slow pointer, right? Now this is just a visual representation. A reality, they are never going to meet like this, at least not at this point, or in the second iteration, if you will. So let's say the fast pointer here is moved to this point, right? So the fast pointer will move twice as the slow pointer, so you move 1, 2, right? The slow pointer will be moved to this point. So let me just put it by the side. The slow pointer will be at this point, right? And the fast pointer will be here. So the slow pointer will move again, and then we'll move the fast pointer twice, right? 1 and then 2. Now at this point they meet, right? They meet properly. So this is where you know, this is where a node can be reached by simply, you know, looking at the next pointers of every other node. So since we are able to, you know, reach a node like this, we will then conclude that this linked list has a cycle in it. Now, but where does this cycle begin is what our next step, you know, involves or entails. So for us to determine where the cycle begins, we need to move our slow pointer back to the head of the linked list, and then we'll begin to shift the 2 pointers one step at a time, right? So we'll no longer move the fast pointer twice as this the slow pointer, but just 1, right? So the slow pointer will be moved like this, and then the fast pointer again will meet the slow pointer at this point. So the cycle began at this point, right? We can conclude that the cycle began at this point, that we can either return the slow pointer or the fast pointer whichever, because I mean they will both meet at the same position, so whichever you choose to return is fine, right? That will be the answer of this problem here, and it's a medium question, which is a really good question to solve. So I'm just going to go ahead and try and implement this quickly for you guys to see how it's done. So I've not solved this yet, right? There's no solution currently, so I'm just going to copy this part here. This is linked list 142, right? So 142, I'll create a file. I'll call this new file. This is leets dash 142, right? 142. It says detect cycle, right? Detect cycle, or linked list cycle 2. Let's just call it linked list cycle, cycle 2. Now I forgot to commit the other solution, so let me do that quickly. So I'll say git add git commit dash m. So this is a linked list question, linked dash list. This is LEETCODE 141, right? Okay, so that's it for that question. So let's go ahead and implement this one. I'm going to remove all of this. Let's remove this. Let's remove this from here, and then why is this here? And then uncomment that part, and then we'll then remove this here. We remove this optional. We don't need it. So I'll be able to perform all these calculations properly. So first step, right? I will just write out step one, determine if lists, if linked list, if the linked list has a cycle in it, right? And then step two would be to get or detect, get node where the cycle is the cycle began. So I'll remove this from here as it's not going to be part of the question. It's simply a note that I'm adding to this question, so there is no need for it to make it to the question, the solution. So I would say, okay, so this is step one. I would say step two here. Okay, so the first step is determining if this if the linked list is actually has a cycle, right? So let's see, has a cycle. I keep saying cycle. Hopefully you get what I'm trying to say. So slow is going to be at the head, right? And then we'll have a fast pointer which will also point at the head like this. And then we want to determine if it has a circle. So if the fast and fast has a next pointer, right, then we can begin to move the slow Slow is going to move by 1. Slow is going to be slow dot next, and then fast is going to be equal to fast dot next dot next dot next. Now, so at this point we are trying to see if the linked list has a circle in it, right? So if slow is equal to fast, right? If the slow is equal to fast, then we'll know this circle has a we'll know this linked list has a cycle. So once we found that cycle, what we'll do is to also determine where the cycle began, right? And by doing so, we'll have to move the left pointer, the slow pointer back to the beginning of the linked list. So slow will become the head, right? We'll leave the fast pointer where it is so that we can move them at the same pace, right, until they meet at the beginning of the cycle, or the beginning of the node where the cycle began. So right, so for us to do this, we'll need a loop again. So this is going to probably be O of n squared time complexity. Not very efficient, at least, but for this question I think it will be. So oh, thank you, somebody said nice code. Right, so let's see. Oh, I didn't see. Thanks, thank you. I'm going to message you after my stream. So yeah. Okay, no more questions. Right, so we are good to go. Okay, so we need to check. So while fast is not equal to the slow, right? Good. The slow pointer, right? While they've not met yet, we'll move the fast pointer just by 1. So fast is going to be fast dot next, and slow is simply going to be slow dot next. Slow dot next. Fast is going to be fast dot next, slow is going to be slow dot next, and at the end we'll return either the slow or the fast, right? So it doesn't matter. Now we have to return it here, right? We need to return it in this in this loop here. So because we're already in detection mode, we know this linked list has a cycle. So once we reach inside of this if statement, the point where that cycle happened has to be returned here. So we need to return it at this point. So we'll say return slow. We can return slow, we can return fast, it doesn't matter. Both of them will be at the same point, so it will still work. Alright, so with that, if we don't return the slow at this point, it means this linked list does not have any cycle for us to even determine where the cycle began, right? So we can then return none here, right? Return none. Can we return none? No, we cannot return none. We have to return we have to return Christ. So how do we return? Well, if we don't see any node, right? Is there a certainty that will always get to the end? So no cycle, right? If there's no cycle, so there is no cycle in the linked list. So what do we return? Node value is going to be between this and that. Number of node in this is going to be 0. I'm still wondering, right? Is there going to be a situation? I mean, if we don't have a cycle, right? What do we return? I mean, this says node cycle, which is very funny because that's not what we want to return. We want to return a list node, right? Or in other words, a node. We need to return a node if we don't see. Um, you know what? Let me just paste my solution and see what happens, right? Let's see what happens, because we still need to know what needs to be returned if none is not a an instance of a list node, right? Of a or we can okay, so let's say I just return a a list node list node with 0 in it. Okay, how about that? Would this work? I'm not sure, but let's see. Okay, something is wrong here. I knew it was going to be this because no output, so expected no cycle. So my output is not in the linked list. Wow. The expected output is no cycle. So what is output? My output say output node is not in the linked list. Well, should I return a string? I don't know. No cycle. Okay, no cycle. Right. And that would be very funny because yes, return value is not a list node type. So okay, list node type, right? Let's see. What if we did this? Return none. This is also not a list node type, so I don't know what else. Oh, okay, it worked. Output contains connects to node 1. Very funny. Very, very funny stuff. I mean, the expected output has to be a list node or at least a node, right? So, I mean, if we're returning none, is none okay? None could be the next of a particular node, right? It's not really, none is not a node or at least an instance of a node class. None is not an instance of a node class. So, returning none is quite weird to me, but let's submit this and see if the solution actually works. Well, it does work, so which is good. So let's go ahead and submit this. So I'm just going to take this here, say git add git commit dash m. This is going to be this is also a linked list question, and is LEETCODE lead dash 141. Yep. No, it's 142. Yeah, 142. So lead dash 142 is the question. I've submitted that, so I need to push this so you can have access to the solution origin main. So the link to the GitHub repo and every questions I've been solving so far is in the description below. You can have access to it and try it out yourself. Okay, so again, when you get stuck at on a question, you just have to look at the solution and try to understand the solution. So here's a question I solved yesterday, um, which was where I found out about the counter, um, this counter module here. I did not know about the counter module before, so yeah, it's really nice to know. So you can try out this. I guess my time is up now, and I will see you guys tomorrow. Let's see, is there any similar question here? So we can find the duplicate number. I'm not going to solve this question though, but I will just have a look at it. Oh, this is an array question. It's not even linked list. I guess. Thank you very much, Sai Kumar. Thank you very much. Thanks to everybody that have been here. You guys are very nice people. Okay, so let's take a look at this question here. Array topic, blah blah blah. Okay, so given an array of integers num containing n plus 1 integers, where each integer is in the range of 1 and n inclusive, okay, there is one repeated number in nums. Okay, return this repeated number. You must solve this problem without modifying the array and uses only constant extra space. Okay, so let's see. This is our array, right? And our array is in, so they say given an array integers num containing n plus 1 integer. What is n? What is n? Is n the length of the array? N plus 1 integers, right? N plus 1 integers. N is definitely not the array, so, the length of the array, because I mean the array cannot contain n plus 1 integers, where each integer is in the range of 1 to n. I don't know, what is n? What is n? In the range of 1 to n inclusive, where each integer is in the range of 1 to n inclusive. That's funny. Let's read the constraints here. I mean, if you look at this example here, it says 1 3 4 2 2, right? There is only one repeated number in nums. Return this repeated number. So this is 2, this is going to be 3. The repeated number here is 3. So I don't know, you might be tempted to iterate through the array and keep track of every number you've seen, or use a dictionary and count which number has been seen more than once. I think that would also work, right? I mean, you can just do counter, count each integer, and for every integer, if any of the integers has been repeated, so you can return that integer. Now all integers in nums appear only once, except for precisely one integer which appears 2 or more times, right? How can we prove that at least one duplicate number must exist in nums? Can you solve this problem in linear runtime complexity? Well, let's see. In linear runtime complexity, we will need to first of all keep track of every number and how many times we've seen them so far. So we can say let's say I'll just put nums count, right, and set it to, let's just count the, so there's a counter class. We can use the counter class, right, and say nums. Let's count every item in nums, and we want in linear time, right? We can say, hold on, let me not just squeeze. We can just do, for so this is just a brute force solution. I can say for nums in nums count, right? For nums in nums count, we want to return return nums if nums, oh, okay, if nums count nums count of nums is superior to 1, just return nums. Return nums. Now I'm not sure if this is the kind of, let's say all integers appear once except for precisely one integer, right, which appears more. So there's at least one integer that appears more than one time. So oh yeah, I'm not really feeling fine, sorry, my voice is really low. Good evening, Ransom. Sorry, somebody, Sai Kumar said, try this, brother. Return sum of n natural. Oh yeah, where some of the list. That is thoughtful. So sum of n, all the natural numbers in the array minus those in the, yeah, that will work too. Well, let's see this, whether this is like a brute force solution. So oh sorry, nums count, oh I'm using nums instead of num, sorry. This is a brute force solution. Okay, so there's a runtime error. What's going on? Expected integers. What's this? This is why I like, coding in my environment first before doing it here. So I'll just use the playground here. Sorry, I'll try to scream a bit. Hopefully my voice is heard, but I can't really shout much today. I am so sorry. So yes, let's do this. Oh, imports from, we can from typing, right, imports lists, and then from collections import counter, right? Okay, so return, oh sorry, I was returning nums instead of num. Christ, what kind of mistake was that? Let's test this out first of all. I'll just take this solution here, bring this back. Okay, so let's say solution is equal to solution. You need to keep coding in Python. Sorry about that. Sorry. Okay, so this is print solution dot find duplicates here. Oh, don't need to pass all of this. Let's see. Yeah, so I returned to here, so this should work, right? It should work at least. Okay, so we've passed the test cases here, which is quite alright. So you can try out other methods on your own to see if you can solve this problem as well. Okay, I'm running late. I'm running out of time, and sorry, ransom about your computer. I don't know. You still have to, keep coding. Anyway, one day you'll get one of those very expensive laptops, and you'll be able to afford them, right? Okay. Thanks to everyone who turned up today to watch the stream. I'll see you guys tomorrow. Bye. Where do I end this stream? Okay. Let me see.